I said previously that generic programming is like polymorphism on steroids. So what does that mean? Well, if you have a business and are trying to determine cost for a product that you have several versions of, it probably makes sense to use traditional polymorphism, to have a class for the general product and then specific subclasses for the different versions. But if you're trying to do something more general, like calculate final cost, which involves taking the sales cost and adding sales tax and credit card charges and so forth, well, this applies not just to some particular product, but to labor and other charges. Rather than create a general class that represents both labor and products, it would make sense to have a generic calculate final cost operation that transcends the individual class structures. In short, whenever you have an idea that's so general that it's not really tied down by any single class hierarchy or idea, that's when we turn to generic programming. Now, while procedural programming orients the program around functions, and object-oriented programming orients the program around classes and their objects, generic programming orients programs around general concepts of data structures and algorithms. You can think of generic programming as a way of defining classes and functions that are not tied to any specific data type. Instead of using a data type, it uses what's called a template. Now, in ordinary English, the term generic often means not special or even not as good, but that's definitely not what we mean here. Instead, we use the term generic to mean that we're generalizing some concept or idea. The hallmark of generic programming are templates. Templates are basically a way of saying that a class's member variables, or a function's parameters, are not of a specific type, but rather are of some generic template type. So, rather than the class or function working only for one specific type, it can be used for any types that match some template. When we actually want to use a specific class or function, we then specify the specific type that the template will take on. For instance, the vector is a templated class. It lets us store a list of any type of object. But then to use it, we have to create a vector that stores some particular type. So, although we've been referring to vector as a class, it's really more than that. It's a more general container, capable of holding a variety of unrelated classes. The angle brackets, like we used when declaring vectors, are used to specify what particular type an instance of a class or function will take on. The type that's specified in the angle brackets is the type that replaces the template type throughout the class or function. Now, decades of work in computer science have let us identify several very general tasks and ideas that work well with templates, things that are very, very widely applicable. The most common of those general concepts are made available to programmers through what's called the Standard Template Library, or STL for short. And, as its name implies, the STL is a library, a collection of templated classes and functions that can be included into the program. It's standard in the sense that there's a clearly defined set of what's expected to be provided in the library. And again, it uses templates, meaning that it's providing generic container structures and algorithms. The STL is likely all you'll need for generic programming. Even in my own work, I rarely find that I want to write my own templated classes or functions. But I use the STL functions all the time. Let me put it this way. A programmer who's not using the STL is missing a huge chunk of the advantages that C++ provides. The STL can save a lot of time in coding by providing efficient implementations of data structures and algorithms that we'd want to use. And the STL is simple to use. Just a pound include gets you access to a generic structure or the algorithms that it provides. The vector class that we've seen before is an example of what's known as a container, and it's just one of several generic containers that are provided in the STL. Containers are classes that collect several instances of some type together in a way that allows certain operations to be performed very efficiently. Now, different containers will have different operations, different member functions, that they support well. The common theme is that they're templated classes, so they can work with many different data types. You specify the type that the container will use when you declare a specific container. For example, vectors are very good for keeping elements in order. The order that the elements in the vector are in is the order that they got pushed onto the back of the vector. It's also very easy to add a new element to the end of a vector. That's the pushback function. Or to remove an element at the end of a vector. That's the popback function. Vectors are also great at letting you access an element at a specific point in the vector. And we refer to this as random access, since we can access any point given at random. We don't have to access them in a particular order. Vectors are very good at letting you say, I want to know the value of the 78th element in the vector, and immediately getting that element. But a vector is not very good at inserting a new element at the beginning, or somewhere in the middle of an existing vector. Say your vector is keeping a list of employees in order of their salary, highest to lowest. If you hire someone at a high salary, you'd want to put that person at the beginning of the vector. And to do this, you have to create a new element at the end, and then you have to copy every element into the space just after itself, and finally assign the value that you want to the new element. That's a lot of copying, and if we have a large vector, the time taken to do that repeatedly can really add up. Now, some real applications have vectors with 1 million elements in them, and having to perform 1 million copies is not something we want to do just to insert one new element. So, let me show you a short menu of the most useful containers, besides vector, that are contained in the STL. You can order from this menu in one of two ways. First, you can call for a container that's implemented in a fundamentally unique way. Besides vectors, such containers include decks, lists, and forward lists. But second, there are also what are called container adapters, and these include stacks, queues, and priority queues. And you can think of a container adapter as something that's not really a brand new container on its own, but it makes use of the other containers to provide some set of functions. It's like taking the engine and transmission of one car and putting a different body on it. The new body might provide different seating and cargo room, and we treat it like a different car, even though underneath it's the same thing. In practice, you use containers and container adapters in very similar ways. Either way, all you do to order from the menu is #include, say, stack. Now, what if we want to keep track of a set of actions that we took so that we can undo back to any point? We can do this using a very basic container adapter that provides one of the most basic operations needed in computing. This is the stack. Think of how a stack of objects works in real life. You have something like books stacked up. Now, there isn't much you can do with your stack of books, but you can take the top book off, or you can add another book to your stack. You can't do things like stick a new book into the middle of the stack. That would risk messing up everything else. A stack is what's called an LIFO structure, which is short for last in, first out. It means that the last thing that we put on the stack is the first thing that comes out of the stack. Well, having a stack in C++ is just about as simple. We can declare a stack of some particular type, and then we can perform one of a few operations. There are really just 4 main operations that we need to do to get everything that we need from a stack. We can push an element onto the stack. This is a member function that takes one element and it adds it to the top of the stack. We can use the top function to see what the element is that's on the top of the stack. And we can also pop an element, which means that we remove the top element from the stack, whatever it is. And we have a function empty that will return a Boolean value that tells us whether or not the stack is empty. Now, like most classes in the STL, there are also a few other functions defined, such as a size function, giving the size of the stack. But push, top, pop, and empty are really the only ones you need on a regular basis. Let's look at a very simple example to illustrate how this works. Notice that we #include stack at the beginning of the program. Then, in our main program, we can declare a stack, S. Since the stack is a generic container, we have to give it a particular type. And in this example, I chose integers. So we write stack, and then in angle brackets, we write int. And then we give the name of the stacked variable, which in this case is just s. Remember that the angle brackets are the way of specifying a particular type, the type that will replace the template in the class definition. We start out by pushing 3 values onto the stack, 10, 15, and 20. That is, we use the member function push, and we pass in the values 10, then 15, then 20 as arguments. And this will create a stack that should have 10 first, so that it's on the bottom, then 15 on top of that, then 20 on top of that. Next is a loop that continues as long as the stack is not empty. We just use not stack.empty parentheses as our condition for the while loop. Each iteration of the while loop, we do 2 things. First, we print out whatever is on top, using the top member function to have access to that top element. Then, we pop off the top element, reducing the size of the stack by 1. And this is done using the pop command. And if we run this code, we indeed see the numbers printed off in reverse order. The 20 that was the last thing pushed on the stack is printed first, and the 10 that was first pushed on the stack is printed last. Now stacks turn out to be a really useful data structure, and most of the time all you need is push, top, pop, and empty to tell us whether or not the stack is empty. For example, imagine you're writing a solitaire card game. In this game, you draw a card and immediately place it on top of a stack of other cards. You can then play a card from that stack, or from other stacks of cards that you have in front of you. In fact, a lot of card games use stacks of cards, where cards get added on top, and they're pulled off one by one. The more you program, the more you'll find plenty of cases where you want to use a stack. Now, an alternative container adapter gives us a first in, first out, or FIFO data structure. This is called a queue, and it's very much like the stack, but instead of the last thing being the one that you can access, it's the first thing in. Queues are used to represent any sort of process where the first thing into the line is the first thing you want out, just like standing in line at just about any store. It's got 4 main operations, just like the stack did. First, there's push, which will add an element to the end of the queue, basically putting that element at the end of the line. Then there's front, which will tell you what element is in the front of the line. It's analogous to the top from the stack commands. Next is pop, which will remove the element at the front of the queue. And empty will again tell us if the container, the queue in this case, is empty or not. Here's a shortcode example, very similar to the one that we had for a stack. Notice that now we pound include queue at the beginning. In the main body of our code, we declare a queue, where the type that we want the queue to hold is an integer. So we write queue, angle bracket, int, angle bracket, then the name of the queue, which in this case is just the letter Q. We can push the numbers 10, 15, and 20 into the queue, just like we pushed them into the stack. And we can have a loop that continues as long as the queue isn't empty. Inside our loop, we'll print the element at the front by using the front member function and outputting queue.front parentheses. And then we remove that front element by calling pop. And with the queue, we see that the elements that came out are in the same order that we put them in. The 10 is first, followed by the 15, and then the 20. Queues are useful anytime we want to process items in the order they arrive. For instance, imagine that you're writing a program to process customers arriving at a business or office. There's a good chance that you'd want to process orders in the same order that they arrived. Whoever arrived first gets served first, and so on. You'd want to keep track of customers using a queue. So at this point, we've seen 3 containers: the vector, the stack, and the queue. Another container is the deque, spelled D-E-Q-U-E, which is actually short for doubly ended queue. A deque is going to work a whole lot like a vector. It's just that instead of only having push back and pop back, It also has a push front and pop front as well. It has basically all the other operations that a vector has. You can get the size using size, or you can make it empty using clear. You can access elements using square brackets with the element number, or using the at command so that you can guarantee you're not reading or writing past the end of the allocated memory. But a DEC is less efficient than a vector, and there's rarely an instance where you really need all the extra functionality that a DEC provides. Now, these containers that we've seen work well for adding and removing new elements at the ends. But what if you wanted to add a new element somewhere in the middle? Or you want to take something out of the middle of the container? So think of how you could cross something off the middle of a grocery store list when you're going through the store. Everything else would stay the same. There's another container called a list that's particularly useful when we want to insert or delete elements at arbitrary points. But in order to understand how to use lists, we first need to discuss iterators. We've seen the idea before of iterating through a vector. We usually have some index, like I, that we put in a for loop, and that we let take the values from 0 to 1 less than the vector length. So we can access element 0, then 1, then 2, and so on until the end of the vector. Well, an iterator is a more general form of that index. It works like a pointer to the element in a container. To use an iterator, we would start at the beginning of the vector, and then we would access element after element until we reach the end. For a container, we can get a begin iterator, which points to the first element. And then we can increment the iterator so that it goes to the next element, then the one after that, and so on all the way through. And finally, we can stop when we reach the end, which will be after the last element in the container. An iterator is going to be a new type that we can use for our variables. When we declare an iterator, we first give the container, such as vector of ints or list of floats, that it will iterate over, then a double colon, then the keyword iterator. And that defines the type of the variable we're declaring. For example, here we've declared a vector of ints where we have pushed back 3 values, 10, 20, and 30. Next, we create an iterator that can iterate over a vector of integers. We'll name this myIterator. So what we write is vector, angle bracket, int, angle bracket, double colon, iterator, space, myIterator. Again, you can think of this as something kind of like a pointer to an element of a vector of integers. We can initialize this by assigning the iterator to the beginning of the container. For our vector, and for many other containers, the member function begin will return an iterator at the first element of the container. In our code here, we write myIterator gets v.begin parentheses. Now, I mentioned before that there's also an end function associated with most containers. The end function indicates a value after the last element in the container. That is, there's not an element at the end, it's not pointing to the last element, but instead it's pointing to some part of memory that we don't care about other than to know that we're no longer in the container. So, in the code here, I'm going to loop as long as I'm not at the end. So I have while myIterator is not equal to v.end. Inside the loop, there are 2 key things that happen. One is that I dereference the iterator. That is, like a pointer, I get the value of the thing that the iterator is referring to. In this case, I output it. So, the first time through the loop, I'll be looking at the first element of the vector, which is the number 10. So, 10 is output. Now, I should mention that there are rare cases where you can have iterators that can't be dereferenced, but these really are rare. The other thing that happens in the loop is that something that's guaranteed to be possible for every iterator, an increment. This is just the plus like we would use for incrementing an index value, and it's okay to write the plus before or after the iterator. This moves the iterator to the next element in the container. So, in this case, we have a loop that causes the iterator to go to every element in the container, and we print it out. That way of iterating through a container, like a vector, is actually very common. So it's not at all unusual to see a for statement that starts from the beginning of the container and iterates through to the end. And since the iterator is usually only defined for that loop, as we loop over the elements of the container, it's common to put the declaration into the for loop itself. Now, there's a feature in C++ that will let you avoid writing the long declaration vector bracket int bracket colon colon iterator. You can just use the word auto, and the compiler will automatically infer the type of the variable needed. Now, you can actually use auto in other contexts too, to get the type of a variable automatically rather than having to specify it. It still has a fixed single type, but it saves the programmer typing. Now, I haven't told you about this until now, since it's better to think about exactly what you're declaring every time you have a variable. And it's easier for you or someone else to read your code and understand the intention. But because iterators are such a pain to declare, using auto in this case is not at all uncommon. And someone looking at the for statement will still understand what the iterator is. Okay. So iterators are important for specifying routines to insert or erase data in a container. That is, when we want to insert something, we give an iterator to the place just after where we want to insert. So if we want to insert at the very beginning, we would use the iterator at begin to specify a position. If we wanted to insert at the very end, we would use the end iterator, which remember is just after the last thing in a container. And that would let us insert there. So here's a short example for a vector. We create a vector with 3 elements, 10, 20, and 30. We then declare an iterator named iter. We set this to begin, and we increment it once, so that iter is now at the second element in the vector. We call an insert command for the vector, passing in iter and the value we want to insert. So this value 40 gets inserted before the second element. Now, if we print out the contents of that vector, sure enough, we see that we've got the elements in the order that we would expect. There's a similar process for erasing data from a container. Now, inserting and deleting are not very efficient for containers like vectors and decks. Instead, there's another container that's much better at handling insertion and deletion. And this is the list, and it has a related form, the forward list. A C++ list is what's referred to by computer scientists as a linked list. Each element exists in a single place in memory, not necessarily contiguous with the next element in the list. Each element has a pointer to the next element in the list. And a doubly linked list also has a pointer back to the previous element also. So, if you're at one element, it's easy to get to the next one. And in a doubly linked list, it's also easy to go to the previous one. And you can easily see how an iterator would go through the list from beginning to end. But a list does not allow you to jump directly to an element somewhere in the middle. If I wanted the 10th element, I'd have to start at the beginning and move forward in the list 9 times to get that element. That's a lot more work than being able to address the element directly with square brackets or the at function, the way we did with vectors and decks. The advantage to lists is that we can insert into them very easily. If we inserted something into a vector, we'd potentially have to be copying huge amounts of information as we basically slide the existing elements down one spot. But with a list, we can just take the new thing to add, update a few pointers, and we're done. Likewise, merging 2 lists is really fast, while vectors or decks would require copying one of the 2 lists. Now, when we type list, we get a doubly linked list. A forward list gives us a singly linked list and will allow pushing only on the front of the list. And insertions take place after the element that an iterator is referring to. For example, say we want to have a list of instructions, such as to make a peanut butter and jelly sandwich. Notice that we pound include list at the beginning. List is templated, so we create a list, and we name it instructions that's of type string. List, angle bracket, string, angle bracket, instructions. We can add elements to the front or the back of a list using push back and push front, just like we could with a deck. So in this case, I've put in 3 steps of making the sandwich. Now, if we left out an important step like adding peanut butter, we can use insertion to add the element in. I've created an iterator that I increment to refer to the second element. Then, calling insert at that point, we'll insert a new element just before the second element. And we can use an iterator to loop through and print out the resulting elements in order. Notice that the instruction we put in the second spot, put on peanut butter, appears in the right place. The forward list is very similar, but we can only call push front or insert after an element. In this example, we push our instructions in reverse order since they're getting pushed onto the front of the list. Then we have an iterator that's set to the second element. When we call insert after at that point, we insert our instruction after the second element. So, printing the whole list gives us our instructions. Notice that now the peanut butter is actually getting put on after the jelly, since the insertion would always come after the element that we were pointing to. Iterators can also make our use of vectors and data structures more powerful by using the for loop in a new way. If you have a class that can be iterated through, we can form a special for loop. Basically, we can set up a for loop that has a variable that takes on the value of each element in a container. The for loop will iterate from beginning to end, and the variable will take on each value in succession. So the syntax for this is to write for, and then in parentheses you have 2 items separated by a colon. The first of these is the variable type and the variable name. When you use this type of function, the variable is only going to be in scope during the loop, so it's not a restriction to make it be declared only in the for statement. Note that you can use auto for the type if you want. However, if you're going to want to manipulate the elements of the container, you should make the type a reference. After the type and variable name, there's a single colon, then the name of the container that you want to iterate through. Here's an example. We have our list, just like before, with the steps to make a peanut butter sandwich. Next, we have a for statement. The container, the list, is made up of strings. So, we're going to have a new variable, step in this case, that is of a string type. And I'm going to want to actually manipulate the elements of instructions. So I'm declaring step to be a string reference, not just a string. Then there's a colon followed by the name of the container, instructions. Within the loop, we can do anything we want to with step, and it will refer to the elements of the list itself. So in this case, I'm adding the string step colon to the beginning of each element. On the first iteration of the loop then, the value of the first element of instructions has step colon added to the front. And the loop ends up adding this to all of the elements. Then we have another loop through all the elements of instructions, this time to print out the results. We set up our loop for parenthesis, auto, step, colon, instructions, close parenthesis. And that just says that we're going to iterate through the entire container instructions, and step is going to refer to the element of instructions on each such iteration. Inside the loop, when we print out the values, we see that they were indeed changed by the previous loop. Now, writing for loops in this way can be a convenient way to access and work with all the elements of a container. Let's review to see if you can figure out which container is the best to use in each of these scenarios. 1. You're running a business and you want to process orders in the same order that they arrive. Well, handling orders in the order they arrive is perfect for a queue. Queues have the first in, first out property. Scenario 2. You're keeping track of movies that you want to see in order from the ones you're most interested in to least. and you want to be able to add new movies that come out or cross off ones once you've watched them. Well, contrary to what Netflix may call it, keeping movies is good for a list. The list lets you easily add or remove movies at any point in the middle. 3. Say you have a long sequence of directions where you want to be able to examine any step in detail. Well, here, the sequence of directions would work well with a vector. Vectors let you easily access any point in the middle. Remember that all these containers are just classes that use templates, meaning that a container can hold whatever type you want. Containers are a great example of generic programming in that they describe a general concept and aren't tied to any particular type. In our next lecture, we'll see more examples of generic programming supported by the STL, associative containers, and algorithms. Associative containers let you group different things together, while algorithms will let you perform more advanced operations more quickly. See you then.